Self-attention, an idea popularized by the 2017 paper Attention is All You Need. This simple equation is at the heart of all the LLMs that we use nowadays. Today, let's try to understand how does self-attention work. First talking about the working of the algorithm, after which we'll proceed to talk about why does the algorithm work at all, trying to understand the underlying intuition behind the idea. Working of self-attention. Let's start with a single sentence, self-attention. This sentence is broken down into tokens. You can think of tokens as words. So we are breaking the sentence into its respective words. Then these words are converted into embeddings. You can think of embeddings as just converting the words into numbers because the computer does not understand words, it understands numbers. If they sound complex, you do not need to worry about understanding embeddings or tokens. You can understand about self-attention before properly understanding about embeddings and tokens. So let us continue. These vectors are then multiplied with WQ, WK, and WV matrices. These matrices are the essence of a transformer. These produce the QKV matrices, which are essential to understand how different words relate to each other. Let's start by creating the Q1 vector. See how the first row of Vex1 vector is multiplied with the first column of WQ matrix, and then the second column, and then the third column to create the individual values of Q1 vector. Similarly, we can calculate the K1 vector, then the V1 vector. Multiplying x2 with the same WQ, WK and WV matrices, we can get the Q2, K2 and V2 vectors. Let's have a look at the equation again to understand what we need to do. Okay, so we need to take the Q vector and multiply that by the transpose of key vector, after which we will need to divide that by the square root of dimension of k. Dimension of k is same as the shape of the k vector. We then take the softmax of this value, which is then multiplied by the v vector. Let's get back to our QKV vectors and start doing what we just saw. We start with the Q1 vector, then multiply it with the K1 vector to get the score 1, after which we multiply it with the K2 vector to get score 2. Let's take some arbitrary value for score 1 and score 2, like 92 and 80. These are just for example, which is then divided by the square root of the dimension of the key vector. This is done to stabilize training. In the original Attention is All You Need paper, the dimension of the key vector was 64. So taking the square root of that will be 8. Dividing 92 and 80 by 8, we get 11.5 and 10. Now let's take the softmax of these values. The equation of softmax is given by this. Inputting the values here, we get 0.82 for 11.5. These values are then multiplied by the v1 vector and the second value is multiplied with the v2 vector. This acts as a regulator, preserving the values of the words which are important with respect to the word for whose attention is being calculated, meanwhile nubbing the irrelevant words. These values are then added together to finally get the attention score for the word self. Let's revisit this part with an example to understand what's really going on. Pramod loves to eat pizza. He ate some last night. Let's try to calculate the attention score for the word he. And when we do, we can see that a lot of the words numb out and the only relevant words left are pizza and Pramod. Because if someone queries a question like, who ate pizza last night? It would be Pramod. What did he eat last night? That would be pizza. Coming back to where we left last off, let's calculate the attention score for the word attention the same way we did for self. I had been very careful about using the word vectors and matrices because in practice we do not deal with vectors, we deal with matrices. So as you can see, we took the word self and attention, created the embeddings for them and concatenated them together to form the X matrix. Now, the way to calculate the Q matrix is very similar to the way we calculated the Q vector. First, we take the first row of X and then multiply them by the individual columns of WQ. Then we take the second row of X and then multiply that by the individual columns of WQ. Similarly, we calculate the K matrix and the V matrix. Now let's take the Q, K, V matrices and plug them into the equation that we started with to get the final attention score. And that's it. You have now just calculated the attention score of your input from a single attention head of an encoder. I say a single because a single encoder has multiple attention head. In fact, the attention is all you need paper had 8. So now we calculate the attention score of the same input through 8 attention heads. For example, we have just taken 4. And after this is done, we multiply that by a WO matrix, which is trained alongside with the WK, WV and WQ matrices. And finally, we get the Z attention score. Here is an image summarizing everything we did so far. Now let's understand, why does attention even work? Imagine you have embedded the following words: apple, the fruit; Apple, the company; an iPhone, and the market. On these embeddings, let's apply some linear transformation and see what happens. As you can see, they are still the same words, but their position relative to each other has changed quite significantly. This helps us get different representation of the same words to understand how they relate to each other in an high dimensional space. How does this help? Let's imagine asking the following questions. Where can I buy an apple to eat? Who makes the iPhones? In these cases, representation 3 will help us answer the questions. Now let's imagine asking another question. Where can I buy an iPhone? In this scenario, representation 2 will help us answer that question. But always remember, these are just linear transformations. We can always go back to the original embedding matrix that we started with using them. And that is all. The reason we do so many matrix multiplication is try to capture all the possible representations that we can have of the X matrix. I have an entire blog talking about transformers, building it up from intuition first and then coding it out. Link in the description. Thank you for watching. That's all for today. Consider subscribing.